Hello. Thank you so much for inviting me to speak to you about a brief history of Colorado. I want to extend my apologies that I can't actually give you this presentation live. Personal issues with my father-in-law came up, and I am going to be on an airplane flying at the time that I was scheduled to speak with you. So thanks for your patience in letting me record this ahead of time. And I want to say that if any of you have any questions that come up, just send them my way and I'd be happy to answer them. So we'll get started with a brief history of Colorado. My name's Lon Abbott. I teach at the University of Colorado, and a lot of the images that you'll see are from a book that I co-wrote with my wife, Terry Cook, who is a science journalist. And let's see oh, there we go. My advance wasn't working for some reason. So I really like to kick this off by saying that civilization, this quote from the philosopher Will Grant, and he says, civilization exists by geological consent, subject to change without notice. And I like to start that way because, I mean, this group knows and loves geology, but I give this talk to a lot of other groups that aren't as invested in geology. And I think that society at large basically just never really pays any attention to geology, and yet everything that we do is underpinned by geology. And so these first few slides, I'm trying to motivate why we would care about geologic history of Colorado. So Colorado's path to state really started with its geology in the gold rush of 1859, illustrated here by this historic photo of people coming into what they called the Pikes Peak gold rush. The gold was found nowhere near Pikes Peak, but that was the only landmark that people in the eastern US knew, and so that really stuck. And it's, of course, geology that gave the state its gold. And I try and illustrate this with, I think this is an image that I really like. This is an 1890s mine operation in Cripple Creek, and it's dwarfed by this tailings pile. This is the modern Crescent mine, where these trucks that are moving 360 tons of ore per load are operating 24 hours a day, 7 days a week, and they're pulling out about $1 million of gold per day from that pit. So resource extraction is certainly still an important part of the Colorado economy, but it's not the be all and end all as it was back in the day. But it's certainly important and a reason why we need to care about geology. We build our cities out of geology, and I illustrate that. This is looking at the Flatirons from my office, actually, and all of CU's campus it's got this architectural homogeneity. It's a Tuscan style architecture, and they use this stone called the Lion Sandstone, which I'll mention later on. And then this old historic church in downtown Denver, and this is made of Wall Mountain tuff, which is another rock that will come into our story later on as well. One of the biggest engines for Colorado's economy now is recreation, and it's obviously geology that provides those kinds of recreational opportunities, both summer and winter. And even more fundamentally than any of that, it sustains us in terms of dictating where water is falling and the geological processes that are turning rocks into soils that we're using to feed ourselves. And I illustrated for the water, you know, here in Colorado, more water falls on the western slope of the mountains than on the eastern slope because of the prevailing wind direction. And so there's this quite active enterprise of piping the water across to the thirsty east slope communities, where places like Denver and Boulder are where they are. So geology offers us great beauty, and that's certainly on big display here in Colorado, but also danger. And so one of the big dangers here is flash flooding. And this is a historic photo by James Balog, who did a master's in geology from our department and he's now a photographer for National Geographic and other sort of high profile publications. And this was the first image that he got published, and he took it when he was doing his master's thesis in the Big Thompson Canyon. And this is the Big Thompson flash flood of 1976. So with that prelude, trying to warm up why we might care about this, how did Colorado come to look the way it does? And so here, for the groups that I oftentimes speak to, they don't know as much about geology. So I'm going to be able to race through these next couple of slides pretty quickly for this crew and just get right to the history. But I like to motivate it by saying, well, first, we use this idea of uniformitarianism, which you have to use with a big grain of salt. Nevertheless, it's extremely powerful. And so it's just that the present is the key to the past. So if, like this 67-million-year-old rock in Golden, Colorado, and it has this pattern here, and it looks an awful lot like this palmetto leaf from South Carolina or Florida, that lives in a completely different climate regime to what Colorado has today. But we use this similarity to say, hey, those palmettos or their ancestors were living in Colorado 67 million years ago, and that would suggest that the climate has changed since that time. So we'll be using modern analogs as we go through here to try and relate what the geologic history, what Colorado looked like in some of its different incarnations over time. The other big paradigm is plate tectonics, the concept that stitches it all together. And for this audience, I don't need to belabor the point, but I just usually in the talks talk about the convection cells in the asthenospheric part of the mantle that's flowing, it's solid, it's flowing slowly, and that's basically moving the tectonic plates of the rigid lithosphere above. And then they can crash into one another, they can pull apart, or they can glide horizontally past one another. So with those concepts in mind, let's go ahead and start with the oldest rocks in Colorado and move towards the present day. So the Earth is 4,600 million years old, but the oldest rocks in Colorado are about 1,750 million years old. For most of Earth's history, what is now Colorado was just a nondescript piece of oceanic lithosphere that got subducted and recycled into the mantle. But about 1,750 million years ago, it was a subduction zone between two oceanic plates. And one oceanic plate was, it was oceanic on the front, but that was also attached to continental lithosphere of Proto-North America. Minnesota was definitely part of that Proto-North America. The closest to Colorado was Wyoming. And the boundary of that Archean Colorado was approximately at the Colorado-Wyoming border. And that plate was subducting, its oceanic portion was subducting underneath another oceanic plate, creating a new juvenile island arc. And the magmas that are produced at subduction zones are higher in silica than the basalt of oceanic crust. So they are really, in terms of composition and in terms of density, which is what's most important for us in this context, they are newly minted continental crust. So that's why our oldest rocks are 1,750 million years. That was when this subduction zone was active. And so in terms of a modern analog, the state resembled something more akin to today's Aleutian Islands, a chain of volcanically active islands rising out of the ocean. And as you can see from this diagram, basically, if this plate was part oceanic and part continental, and so if my this hand is the plate that Colorado is built on, the overriding plate, and you've got the subducting plate coming down, and if my bare arm is the oceanic lithosphere, and my shirt-sleeved arm is the continental portion of that plate. As you subduct the oceanic lithosphere, the continent, Wyoming, or Proto-North America, is getting closer and closer and closer to the subduction zone. And about 1,700 million years ago is when that continental lithosphere of Wyoming entered the trench, and it evolved into an arc continent collision. And that appended what was then Colorado, or that volcanic arc that is what we now know as Colorado, onto North America, where it's been ever since. And that raised a coastal mountain range. And probably the most famous example of one of these arc continent collisions today is the island of Taiwan, where the passive margin of China is entering into the subduction zone, or excuse me, the Luzon volcanic arc, which is what makes the Philippines, is colliding into the Chinese passive margin to form the island of Taiwan, which has mountains that rise up to 13,000 feet, pretty much right from sea level. So gneiss and granite were formed, and these are the kinds of rocks that we're able to use to tell the clues. Gneiss is a foliated metamorphic rock, high temperatures and pressures, but most importantly, under differential stress, that is going to line up the minerals and foliate the rocks. And then those magma chambers that were feeding those intermediate silica stratovolcanoes and calderas of the volcanic arc, those were intruding granites. So we've got a lot of granites in the Colorado mountains, and we've got a lot of these gneisses and schists. And when you look at the age of deformation and metamorphism, those are all checking in around 1,700 million years old, and many of these granitic plutons are the same age. So this is an example of sort of what Colorado would have looked like in the Paleoproterozoic 1,700 million years ago in comparison to a modern analog. And here Australia is separating from Antarctica at a divergent plate boundary. By plate tectonic standards, it's trucking northward really quite quickly. And as it does, it's impinging on the Eurasian plate, which most of Indonesia is part of, as well as the Pacific plate. And so here you've got a subduction zone through Indonesia. You've got a subduction zone down through here, the Solomon Islands, the Vanuatu, places like that. But in two locations, the Australian continental lithosphere has actually reached that subduction zone. One is on the island of Timor, and the other is here in northern New Guinea. And so I actually did my graduate work here on the north coast of New Guinea, studying the world's youngest mountain range that has been raised up to about 13,000 feet as well, like Taiwan, right out of the ocean. It's called the Finisterre Range, and it's this modern youngest arc continent collision. And that is a good modern analog for what Colorado looked like with the chain of volcanic islands. Here is Proto-North America encroaching in. Everything that is in this sort of tan color is continental crust and lithosphere, and everything that's gray is oceanic. So you've got this juvenile continental material, and then you, just like a bug on a windshield, you smack it in North America as you try and subduct the North American plate, which is too buoyant to do, and it just won't go. All right, so we, of course, as geologists, use the rocks and the clues that the rocks give us to tell the story. And so if we have a gap in the rock record, we have gaps in our story. And so the next real rock record that we have, we've got to skip forward about 300 million years to 1,400 million years ago. And this is a huge outpouring of granitic rocks in the Colorado area. It's called the Berthoud granites. It used to go by the name Silver Plume granites, but now they've changed it to Berthoud, named for Berthoud Pass. Silver Plume is a mining town that people pass on the way to the ski areas on I-70. Berthoud Pass is another place that a lot of skiers go over. And all of this is these 1,400 million year old granites. A couple other examples. This is Long's Peak, the highest peak in Rocky Mountain National Park. And essentially every granite that you see in Rocky Mountain National Park belongs to this 1,400 million year or 1.4 billion year suite. And then this is Mount Evans, the summit of Mount Evans. This is what the rock looks like, and it too is a 1,400 million year old granite. And a lot of people see that because that's the highest automobile road in the US, going up over 14,200 feet up on a paved road. And so these granites at 1,400 million years are a real geologic puzzle, and they're by no means restricted to Colorado. This is something that you see these all the way up through the mid-continent of the North America and all the way up into the Baltics. You see it in Antarctica. 1,400 million years ago was one of the biggest granite producing events in the history of the world. And it is a geologic puzzle. They are what used to be called anorogenic or now A-type granites that don't seem to be associated with any kind of tectonic activity or not orogenic activity. And there's a lot of debate about how they formed. We've got another 300 million year gap in our record until we get the next big rock representative, and that's the Pikes Peak granite. The 1,700 million year old granites that were the guts of this volcanic island arc, and then the 1,400 million year granites, those are spread across Colorado with a lot of different intrusions that are unique or specific to one locality, but there's dozens of them. The Pikes Peak granite is quite different. It's by far the biggest batholith in Colorado. And so in that regard, it's unique. But it's really, really large. It's much more than just Pikes Peak. A lot of the mountains west of Denver consist of the Pikes Peak granite as well. It too is one of those anorogenic granites or A-type granites. In fact, its chemistry was used to define A-type granites when the concept was first proposed. And we're not sure exactly what caused it. It was being emplaced at about the same time as the mid-continent rift, which you all are familiar with in a big way, running from like Lake Superior down through Kansas. And it seems like it's probably associated with the mid-continent rift in some way, but how has not been connected yet. Our next, we've got another big gap in time until about 600 million years ago. And we've got not very many from 600 million years ago, but we do have interesting ones. Each one of these stars is a diatreme that some of them are kimberlites. And so they have diamonds in them, not all of them, like this one by Boulder doesn't. But in particular, these up at the state line of Wyoming, these are called the state line diatremes. And diamonds were first discovered there to the surprise of the geologists who discovered them in the 1960s. And it turns out Colorado was the first place in North America to produce commercial diamonds. Although there aren't a lot of them and they're not of particularly high quality. There's not a lot of these, that De Beers is going to be selling in the jewelry stores. It's more industrial diamonds. And so the mines right now are shut down, but they may come back at some point. The supercontinent Rodinia was assembling about 1,100 million years ago. And that mid-continent rift and the Pikes Peak granite were temporally associated with that. All supercontinents, once they assemble, they're inevitably going to break apart again. And so as those diamond pipes were being erupted in Colorado, the Rodinian supercontinent was starting to break apart. And as it was, the sea began to rise. Australia and Antarctica, which were our neighbors prior to that, started moving off to the west, opening, I'm talking in modern geographic coordinates, as the Pacific Ocean opened in between. And so the sea started to flood in from west to east. as Rodinia was splitting apart. And so by 500 million years ago, Colorado was on the coast, and that is illustrated here. So it was a beach sort of setting, a modern analog. And we see that really nicely. This is in the city limits of Manitou Springs, which is a suburb of Colorado Springs. This is the Pikes Peak Granite here, and it's overlain by what's called the Sawatch sandstone. And it's got symmetric ripple marks and all kinds of other indicators that this is a beach sand. That transgression, that rise in sea level continued. And as it did, what was beachfront property was covered up by the sea. And so here, this is a place called Williams Canyon, which is right near Colorado Springs. This reddish rock down here, that's that Sawatch sandstone. And then it is overlain by the Manitou limestone, which is this stuff that makes these steep walls. And this is the visitor center for Cave of the Winds. Not an especially spectacular cave, but it is a show cave, and it's one of the better ones we have in Colorado. So there's inside Cave of the Winds with some of the stalactites, and it's all formed out of this Ordovician Manitou limestone from this transgression as Rodinia was breaking apart. Transgressions and regressions continued, the sort of slough sequences that alternately covered the continent and then regressed, leaving unconformities. But everything was pretty quiet for about 200 million years in Colorado. We were just a passive continental margin with oceans rising and falling. But then about 300 million years ago, tectonics gave Colorado mountains again. And I choose to illustrate this with this picture of the modern Sangre de Cristo Mountains. And it's not that the modern mountains were formed at this time, but all these rocks that make up the Sangre de Cristos in this view, these were all debris that was shed off the ancestral Rocky Mountains. So this supercontinent cycle, once you break up the previous supercontinent, you start the clock running on the assembly of the next supercontinent. And so, of course, the next supercontinent after Rodinia was Pangaea, the most famous supercontinent of all. And it was assembled on the order of about 300 million years ago. The primary North American manifestation that was the Acadian orogeny, which raised up the continent-continent collision between Gondwana and Laurasia. And so the West Africa, Northwest Africa was colliding with the East Coast to raise what was likely Himalayan scale Appalachian range. And then Venezuela, part of South America, was tucking itself into the Gulf Coast to raise the Ouachita Mountains, which are really just an extension of the Appalachians. And Colorado was sort of out of the fray, and so it wasn't raising the mountains at the time, but sort of peripheral to that, you rose smaller mountains, the Ancestral Rockies, off to the west of the Ouachitas. And these sort of blue-green areas, that's showing the footprint of the Ancestral Rockies. There were two main ranges. This was called, typically is named Uncompahgre, for the Uncompahgre Plateau, which is right here. And this is usually called Front Rangia because it was on the footprint of what's today the Front Range. And I try and impress upon people that they're called the Ancestral Rockies because they rose in approximately the same location as the modern mountains, but not exactly. So look at all this area near the Aspen area, for example, that's mountainous today, but that was a basin in Ancestral Rockies time. And conversely, the highlands were going all the way to sort of Amarillo, Texas, the panhandle of Texas, and far southeastern Colorado, which today is emphatically not mountainous, but it was back then. And some of Colorado's most colorful rocks date from this episode. So with me at University of Colorado here in Boulder, our flat irons are sort of the ones we love here. These were alluvial fans and braided rivers that were being shed out of the Ancestral Rockies. This is balanced rock at Garden of the Gods near Colorado Springs. same formation. These are the crestone peaks right here in the Sangre de Cristo Mountains. And as I said, those are all sedimentary rocks that are the debris shed off those mountains. And the maroon bells, which are maybe more iconic than any other mountains in Colorado, on gracing 1,000 postcards and calendars. And these are all very different from your typical Colorado mountain in that they're layered sedimentary rocks. And these are also Pennsylvanian to Permian age rocks that were mudstones and sandstones that were shed into, if I go back into this shallow seaway that existed in between the two main strands of the Ancestral Rockies. And so the Ancestral Rockies would have looked simultaneously very familiar and utterly foreign, as illustrated here. I love this book called Ancient Denvers by Kirk Johnson and Bob Reynolds. And they did this when they were at the Denver Museum. Bob is still at the Denver Museum of Nature and Science. Kirk Johnson now runs the Smithsonian. But they teamed together with artists to make scientifically defensible paintings of what Denver looked like at different times in the past. And so about 300 million years ago, this is the picture. These are the Ancestral Rockies. We don't know exactly how high they were, but probably in terms of vertical rise, similar to the modern mountains, but almost surely not anywhere near as tall above sea level, because we're starting from a tropical sea. So we were, Colorado at that time was at about 10 degrees north latitude, so it was tropical. And the fountain formation is shown here in the red, and these are the braided stream and alluvial fan deposits. But then you started to accumulate mudstones in these seaways off to the side, and we know that very well. They've been pierced by a lot of wells that have been drilled for the petroleum in the Denver Basin area. And so it was a warm place, and these mountains probably weren't all that high above sea level, maybe 5,000, 6,000 feet above sea level. But despite the overall warmth, they might have endured some periodic cold spells. This was the time of the late Paleozoic glacial episodes. So global temperature was cooler, and these polygons here that are found in a number of places in the fountain formation have been interpreted by some scientists as being like pattern ground that you would get in a paraglacial setting. Well, those Ancestral Rockies rose about 300 million years ago, and already by 285 million years ago, they dwindled to just mere foothills. The climate got even more arid, and Colorado was enveloped by a desert of Saharan proportions. So here again from ancient Denvers is what Denver would have looked like about 285 million years ago, with these big sand dune fields. But there are some rivers that are still eking their way out of what are now the foothills of the Ancestral Rockies and crossing the dune fields, very similar to the Medano Creek, which is the creek that flows through the Great Sand Dunes National Park in the Colorado Rockies today. So Colorado's landscape at that time was dominated by sand dunes, and we see that from the large-scale crossbedding in these well-sorted fine-grained sands that we see called the Lions Formation. And I've showed you balanced rock at Garden of the Gods before, but the main scenic grandeur of the Garden of the Gods, these towers, these are vertical bits of Lions Formation sandstones that are stood up. And so there's another picture of the sort of Tuscan architecture at the University of Colorado. This is the building, the geology building on campus. And it looked like all the other buildings faced with this Lion sandstone. And this is a quarry in the Red Rocks open space in Colorado Springs where they mined the Lion sandstone. So most of us in Colorado encounter some of these ancient dunes every day, from the buildings to a lot of flagstone patios. You go to 255 million years, so only 45 million years after the Ancestral Rockies had been raised, they were pretty much erased from the landscape entirely. Sea level had risen It was still very, very hot and dry. And we see that with these stromatolites. So this is called the lichens formation, and it's got these stromatolites, which are bacterial mats. Here's again from ancient Denver's what Denver would have looked like at that time, with this sort of tidal inlets that were just populated by all these stromatolites. And this is Shark Bay, Australia, where some of the the most famous easily stromatolites in the modern world are. And so that's the modern analog for the sort of tidal inlets that would have dominated Colorado's Front Range at that time, as revealed by the presence of these stromatolites. There's another gap in time, about 100 million year gap in time before we get to the Morrison Formation. And this is the Morrison Formation, which is meandering river deposits, really low gradient, and a lot of paleosols, floodplains that gives you this multicolored look to the mudstones. There's a meandering river channel encased by these floodplain muds. And this is actually the place of quarry that during the Bone Wars in the 1800s, Cope and Marsh, who were preeminent paleontologists and hated each other's guts and were trying to outdo each other in finding any kind of fossil life at all. And they really turned their attention on Colorado after one of the mines professors, a guy named Arthur Lakes, found a bone in Morrison, Colorado, and sent it to, unwittingly sent it to both of them. And that just turned their laser focus on the American West, Colorado to begin with, and then they extended out wherever there was Morrison Formation. This is Allosaurus, and this is Stegosaurus, both of which were first discovered and described in Morrison, Colorado. Stegosaurus is the Colorado state dinosaur. Then another 50 million years later, another sea encroached on Colorado about 100 million years ago. And this was due to the breakup of Pangea, which started about 200 million years ago, but really was cooking along well by 100 million years ago. And this is Dinosaur Ridge, where we've got this really, truly spectacular trackway just right in suburban Denver. These are ornithopod dinosaurs, the duck-billed dinosaurs, and they were walking along a beach in herds. And then here are ornithomimus. These are little turkey-like sized predators that were preying on them. This is at Skyline Drive, which is near Canyon City. And this is the bottom side of this same formation, the Dakota Formation. And these are Ankylosaurus footprints looking down at the underside. And then here are some symmetric ripples from those beaches. That transgression continued to move forward, and so Denver was buried or was drowned by the sea, the Western Interior Seaway that stretched from the Gulf of Mexico all the way up to Hudson Bay. Here are some of the shells from that. These are inoceramid clams, and this one is encrusted with a bunch of oysters, these sort of parasitic oysters on it. So those are the kinds of evidence. And then here again from ancient Denver's sort of an artist's reconstruction of what Denver would have looked like at that time, about 90 million years ago. There was very low oxygen in that ocean, that Western Interior Seaway. And so we've got a lot of black shales like this one right here. And that was buried in the Denver Basin down into the oil window, a couple, 3 kilometers down, where it's able to cook out and produce oil. And this is actually this is an oil rig. This was the first oil rig from the Boulder oil field. Boulder is not a hotbed for oil exploration now, but this started pumping in 1901. And this was still pumping, is my understanding, when they shut it off in 1994, it was still producing about 1 barrel of oil a day. And so now it's on the National Register of Historic Sites. And one little tidbit that a lot of people don't know is that the down by Florence, Colorado, near Canyon City. That was the world's second commercial oil field after Titusville, Pennsylvania. Those seas that rose during the Cretaceous, and as the Cretaceous was coming to a close, they started to retreat. And the last sea retreated from the Front Range 68 million years ago, and it deposited something called the Fox Hill Sandstone, a beach sand again. This is an outcrop of it right where I-70 starts climbing up into the mountains. And this is just east of Boulder at a place called White Rocks Open Space, where you see the same stuff. And part of the reason for that was that global eustatic sea level was dropping, but there was a really important local activity that was going on, and that was the rise of a new mountain range that is the sort of, it's the foundation of the mountains that we know today. And it's called the Laramide orogeny. So it tilted and buckled the rocks along lengths like the flatirons of Boulder, Garden of the Gods, which are stood up vertically. This is Roxborough State Park, southwest of Denver. And it injected a bunch of mineral-rich intrusions in something called the Colorado Mineral Belt, which runs from Boulder down towards Durango here. And every one of these red dots is an important mineral deposit that was mined. And that's what caused the gold rush of 1859, and people calling Pikes Peak or bust. We're still dealing with the after effects of the mining. There is still mining, as I said before, but it's a much smaller part of the economy. Nevertheless, there's a lot of environmental issues. We don't have a lot of limestone here to neutralize acid mine drainage. So this is like the Argo Tunnel, which is coming out in Idaho Springs, one of the big mining areas. And this water has a lot of dissolved heavy metals in it because it's got a pH of about 2.5. And this is where the Department of Environmental Quality, the Colorado Department, is pulling this heavy metal sludge out by just neutralizing the acidity of this and then carting those to a toxic landfill. By 37 million years ago, those Laramide Rocky Mountains had been eroded to an undulating surface with very low relief. This is up on top of the modern wet mountains of Colorado, and you're up here at 11,000 feet, and yet it's just very, very flat at that high elevation. And this is a remnant of this Rocky Mountain erosion surface that wore those mountains down. Right after that, the state was engulfed by one of the biggest volcanic events the Earth has ever witnessed. Again, from ancient Denvers, this is an illustration of the Wall Mountain Tuff. The Wall Mountain Tuff was erupted in the area around between Buena Vista and Salida, Colorado, and it is one of the biggest ash flow tuffs known. And it rolled across Castle Rock area in the Denver area, probably in about an hour. And this is trying to show this. There's the San Juan Mountains. There's 15 different calderas, including the biggest caldera ever mapped in the San Juan Mountains. And they go all the way to Rocky Mountain National Park. This is Trail Ridge Road. And as you go over Trail Ridge Road from the Front Range, you look at this mountain range, which is the Never Summers Range. And all of those are a bunch of granitic intrusions that are the magma chambers that fed a bunch of ashes. This is the Specimen Mountain area, and that's a bunch of ash flow tuffs there as well. And this was called the Ignimbrite flare-up, and it was going on between about 37 and 23 million years ago, and it buried that Rocky Mountain erosion surface. One eruption unleashed a volcanic mud flow that dammed a river, and it formed a lake called Lake Florissant. So these little hills are remnants of what used to be a stratovolcano that is up, that's an estimate of what it would have looked like. It dammed up a river to form Lake Florissant, where you get these paper shales. The ash buried some sequoia trees that were growing there and petrified the bottom about 15 feet of their trunks. Everything else decayed away, but these are petrified. And basically in that lake was pond scum of diatomaceous mats that insects and leaves would get trapped in. And we've got one of the world's best insect collections, fossil insect collections, because of that. So those Laramide Rocky Mountains were buried both by ash from the ignimbrite flare-up and their own debris as they were eroding away. So if this is what Colorado looked like during the Laramide orogeny about 65 million years ago or so, it would have looked very, very similar to what it does today, with the Great Plains, some eroding, tilted sedimentary rocks, and then the crystalline rocks that are most of the rocks of the Colorado Rockies. But by 5 million years ago, we would have been in a high elevation, but most of the state would have looked an awful lot like the Great Plains, quite flat with maybe just a few little foothills poking up. Here's an example of that. This is called the gangplank. This is right up by the Wyoming border. This is all the tufaceous material that was deposited during the Eocene in the ignimbrite flare-up, Eocene and Oligocene. And then here in the Miocene, this is called the Ogallala Formation, very important for aquifers. And this is a close-up of what the Ogallala looks like. And it's got a bunch of debris from the Rocky Mountains in it. And so this is just covering the modern mountains, and that's where I-80 goes over the mountains. And I-80 is a much easier way for trucks to get over the mountains because they're still buried in this debris. I-70 used to look like that, but it doesn't anymore. And the reason is that in the last 5 million years, this sediment cover in Colorado has been excavated. And as it's done so, it's revealed those old Laramide mountains. The old Laramide mountains were made of these crystalline rocks that are resistant to erosion. So as you erode the sedimentary material, you hit down onto the crystalline rocks and they erode much more slowly. And so the relief of the mountains that is so dramatic on the Front Range today has been created. And this was aided greatly by massive mountain glaciers with the Pleistocene Ice Age. And this is maybe the last point to leave with in terms of this, is that the modern mountains, there's a big controversy as to what caused this excavation event. Was it a more recent period of tectonic uplift of the mountains for which we don't have any faulting evidence or anything like that? So it'd be a much more passive, a pyrogenic rise of the mountains. Or was it due to climate change? Climate certainly played a role, but was it the be all and end all, or was that just helping and facilitating the tectonic uplift? That's one of the things I do for my research, is trying to answer that question, me and a whole lot of other people. But however it happened, that excavation event created Colorado's mountains, canyons, and plains, and they took their current form just in the last 5 million years. So while this is an ancient landscape in terms of the rocks, it's a very modern landscape, geologically speaking, of just really forming in the last 5 years for all of us visitors and locals alike to enjoy. And I like to finish this with this picture of my son. Years ago, he's in college now, but enjoying one of the Colorado 14ers. So thanks very much, everybody. I will stop sharing and take any questions that you might have.
Okay, I can start with the first question.
Sure.
In terms of, say, the Front Range of the Rocky Mountains, so most of the uplift was Laramide, and it was done about 65 million years ago. Is that?
Well, so the Laramide orogeny started, it depends exactly where you are, but in the Front Range, it started sort of about 65, 70 million years ago. And it was still going until about 45, but it was done by then. And so what we now know of as the Front Range, it's bounded by these faults these are reverse faults. So due to plate compression, and that formed, and you piggyback those crystalline basement rocks up over the rocks, the Paleozoic and Mesozoic sedimentary rocks during the Laramide orogeny at that time. But then the story gets a little more complex. It's not just that then the mountains have just sat there since then, because we've got this really good evidence that they got eroded away. And many people think that they may have been eroded down practically to sea level. Certainly not to sea level, because we don't have any more marine rocks. But a lot of people think, well, maybe Colorado in the Eocene or the Oligocene was just a few hundred meters above sea level. Other people think it was much higher. Paleoaltimetry is a really squirrely business, and so we really don't know. But what we do know is that they were buried. Whatever their elevation was, they were buried, and then they've been re-excavated just in the last 5 to 10 million years. And so one of the big controversies is, well, why were they re-excavated? Was everything really high? And now we just climate change has excavated that out and basically exhumed the Laramide Rockies, because the modern mountains look much like the Laramide Mountains did, but they are not just due to that because they had to be re-exhumed. Or was it that you've raised the area tectonically, and so the actual elevation above sea level of Colorado has gone up in the last 5 to 10 million years? There's two camps that very much disagree with each other about that. And so it's sort of an interesting aspect, and one that I and many other people are trying to work on.
Okay, is there any current uplift that can be measured using GPS, say?
Well, so yeah, you can do things like GPS, you can be re-leveling and whatnot. But so one of the faculty members in our department, Peter Molnar, who's a world-renowned expert in mountain building, he and Phil England, his colleague, have a paper that's really seminal in the mountain building community from 1990, where they really make the point that you could go out and survey all these monuments with GPS. You can go back and resurvey them. And if, say, Long's Peak is going up, you can say, well, then there's modern uplift, that the Rockies are rising. But isostasy is always in force. And so we know that there's been erosion. And so if there's erosion happening, you're going to get isostatic response to that. And so because the isostatic response is not, local peak by peak, but it's broad, if you're not eroding Long's Peak very much, but you're eroding the canyons near it, Long's Peak is going to go up. But it's going to go up isostatically, not because of some tectonic impetus. It's a subtlety it can be confounding, but it's really important, because if one is saying, hey, there's some tectonic thing that's going on in the last 5 to 10 million years that's causing Colorado to get high, you can't confirm that just by going in and resurveying monuments, because those areas of the landscape will be going up, but you've got to see what is the elevation change of a much broader area called surface uplift, because it's like about 100 by 100 kilometers or so is usually thought to be enough to sort of get away from things like this isostatic adjustment.
Okay.
Did that make sense?
Mhm.
It's a tricky point.
Yeah, and then a related question. I read somewhere, I can't remember where recently, that the thinking is that the uplift of the Colorado Plateau is relatively recent.
Yeah, well, so there's no major through-going faults that separate the Colorado Rockies, the Colorado Plateau, and the Great Plains. And so when you're talking about Cenozoic changes in elevation, those three provinces are basically we think they're going in concert. If you have real broad wavelength, you could have tilting. So more tilting in the Colorado Rockies than, say, the Colorado Plateau or the Great Plains, but no big, differential like, oh, the Colorado Rockies popped up and the Colorado Plateau didn't. And so what I described about this sort of fight about old versus new, recent attainment of the current elevations, everything I said about the Colorado Rockies pertains to the Colorado Plateau, and they're really kind of linked. So yes, the people who think the Colorado Rockies went up recently also think the Colorado Plateau went up recently. And the people who think that the Colorado Plateau was up high since the Cretaceous, they think the Colorado Rockies were up high since the Cretaceous. And there are some people that are kind of in between.
Okay. And then I read a book a long time ago by a plate tectonics denier named Don Barr. Are you familiar?
It's probably Donald Bars was a professional geologist, and he wrote a lot of books about the Colorado Plateau in particular. And yeah, I remember some of his writings that he was not too keen on plate tectonics.
But one thing he talked about a lot was lineaments.
Yeah, he's big on his lineaments.
And I guess they can be detected geophysically, I guess.
Geophysically, a lot of times, even just topographically, you'll see lineaments. One good example of that is you look at the Arkansas River, and it flows down the Rio Grande Rift from Leadville down to Salida. And then from there, it turns east. And as it goes east through a thing called Bighorn Sheep Canyon, boy, it is really straight as an arrow. And you can just see on any kind of DEM of Colorado, wow, that's running along a lineament. Yeah.
They will. Can you define that term, lineaments?
Yeah, it's just, it's sort of a generic term for anything that's very linear. So you could see it, as Randy said, geophysically. You can see it topographically, and it's just something that's really, really linear. And the idea is that, okay, those are, you're inheriting in the modern topography things from, say, like faults that are from Precambrian or something like that. There's no question that those lineaments exist. But whether or not that can be that can explain everything that you see in Colorado. Don Bars wanted to do that. I and most practicing geologists are skeptical of that.
Okay. Yeah, I guess when you're talking about 1700 million years, the suture zone between Wyoming and the island arc Colorado, I wonder if that suture zone is still visible as one of his lineaments, for example.
In places you do see lineaments. Other places it's not as obvious of a lineament, but certainly geologically you can see it. Okay. Yeah, and there are others as well. So I obviously had to simplify the story quite a lot. So that volcanic arc that made Colorado, it smashed into the edge of the continent along the kind of Colorado-Wyoming border. That's called the Cheyenne Line. And then about 100 million years later, another very similar volcanic arc smacked in, and that added New Mexico and southern Arizona and all that. You could see that line, that plate boundary, was running from northeast to southwest. And so if you go hiking in the Grand Canyon, you go to the Vishnu schist, the Zoroaster granite. Those are the same 1700 million year old granites, gneisses, and schists that we have here. And they were added in this, what's called the Yavapai orogeny, named for Yavapai County, Arizona, which is in sort of central Arizona. And then the Matazal orogeny, named for the Matazal Mountains, which are just east of Phoenix. That was the docking of that next arc terrain. And it added and moved the coastline even further south. And basically there are lineaments associated with that suture zone as well. So one of them is the Jemez lineament, and that is seen as a chain of young volcanics from Mount Taylor in New Mexico, just north of Interstate 40, through the Jemez caldera, the whole Jemez Mountains, Valles caldera, and the Jemez Mountains, and then all the way up through Raton, the Raton mesas, where there's a bunch of basalts, up to like Capulan volcano in Mexico is one of the youngest ones that's a national monument. So that's another way the lineaments may manifest themselves, is focusing volcanism.
Mm-hmm. Okay. Oh, just as an aside, when you were talking about the San Juans, I did my geology field camp out of Gunnison, Colorado, back in the late
Oh, yeah.
70s. And it seems
Yeah.
like all we mapped was tufts.
I bet. Yeah.
Yeah, it got kind of boring, actually. It's just one tuff after another. We didn't really see anything but tufts. So,
Well, maybe that was partly due to the fact that your instructor was really enthusiastic about tufts, because there are a lot of tufts there, but there's certainly, you go north of Gunnison and you get out of the tufts pretty fast. So,
oh, okay.
but yes, from the south, from Gunnison south, boy, tough and more tough, because you're on the San Juan volcanic pile from that ignimbrite flare up.
Mhm.
And actually, one of the things I'm doing research on right now, I'm presenting it at the AGU conference in December on it, is that if you go north of Gunnison towards Crested Butte
Mhm.
into what's called the West Elk Mountains, in the ignimbrite flare-up, that was sort of a satellite volcanic area, and it looked just like the San Juans. But now all that's been eroded away. And so every one of these mountains that you see there, like the Crested Butte ski area itself is a great example. And there's about 24 of them around. They're all these big granitic laccoliths. And they were intruded and they were sort of feeding the volcanoes, but the volcanoes are now eroded away, as are all the sedimentary rocks that they intruded into. And so you've got these very isolated mountains. So the topography there is quite different from your typical Colorado mountains. And it's sort of what the San Juans will look like once all those tuffs are eroded away. And so the question we're trying to track down is, well, why, if these two areas were so similar in the ignimbrite flare-up 35 million years ago, why did the West Elks get eroded to the tune of several kilometers and the San Juans didn't? We don't have an answer yet, but that's what we're working on.
Oh, and one other question I had, you mentioned the Oglala sandstone, and it was at the surface where you showed it at the, I forgot the term you used.
The gangplank, yeah.
Gangplank.
Yeah.
And in the Great Plains, it's well down in the subsurface.
Yes.
So the area of the gangplank, would that be the recharge area for the
Yes.
Oglala?
Yeah, that you're absolutely right. That is the foothills and flanks of the Rocky Mountains are really the recharge area for the Ogallala aquifer.
And are there efforts being made to protect that aquifer in terms of what can be done at the surface where the recharge is occurring, since it is such an important aquifer?
There are people who are trying, but how much traction they're getting, it's certainly not a big front burner issue. That there's a tremendous amount of sort of community support to say, yeah, we don't want to pave over the whole recharge area. And of course, the discharge is still going apace. And so the things that I've seen are people are giving the aquifer about 20 years and then it's going to be dry.
Wow.
Yeah, so that's a huge issue.
Yeah,
but
especially since
it's a complicated issue, and so the geologists are raising the alarm, but that doesn't mean that policymakers are doing anything about it.
Yeah, and the fact that the recharge is in Colorado and then the use is in the Great Plains states.
Yeah, but even in Colorado, it's affected as well, because you go sort of far enough east and you get enough rainfall that you could farm even without irrigation. But boy, in eastern Colorado, you've got to irrigate, and they're tapping the Ogallala aquifer. So it's not just Kansas and Nebraska and Oklahoma that are and the Panhandle of Texas that are relying on this. All the farmers in eastern Colorado are as well.
Oh, okay.
But that isn't enough to really catalyze the the discussion. I mean, so much of this is so much out of the realm of the science and really into the policy of how water law, there's a distinct difference between the way water law treats groundwater and the way it treats surface water. And we certainly have had some lawsuits like between Colorado and Kansas and Nebraska, and I can't remember who sued who, but about those water rights, and some of the farmers in Colorado can't draw out of their wells because that would then lower the groundwater table for recharge for the folks downstream. But it's all about the groundwater versus surface water. It's the Republican River and the Arickaree River, some of these smaller rivers that are going into the plains.
Okay. Okay, well, I'll quit asking questions. Dave and Joni, do you have anything?
Hey, Randy, I'm Steve Erickson here.
Oh,
joining us.
Steve. Oh, okay. Hi, Steve.
Just got in from work. Lon, I want to thank you very much for your cooperation on all of this. Hope you and your family all the best. And
Thank you so much, Steve. I really, really appreciate it. I'm so sorry that it's interfering with this, but yeah, like you say, we've got bigger things on our plate. Unfortunately, it's mostly my wife because it's her dad that's having a tough go.
The real world has a tendency to intrude. That's all there is to it.
Unfortunately,
we
yeah.
actually, a number of years back, about 20, 30 years ago, I think it was, they had a guy who had a heart attack the day before the talk. So they had to do a round scramble there too. So we expect the unexpected. And sometimes when we have the meetings at school, we have to close down because of blizzards and stuff like that. That happens too. So
Sure.
Thank you again for your assistance and your support. I'll be interested to hear the whole talk when I get a chance on Monday night, and I'll let you get going then.
Well, thanks a lot for tuning in, and I hope when you get to hear the whole talk that it's worth your time. I really appreciate the society inviting me to speak.
Yeah, and who would be a good speaker about the Ogallala Aquifer?